So we have discussed general second order system. Okay? We have looked at general second order systems. Today what we'll do is, we'll look at an under time second order system. So what was the general second order representation? General second order system representation. We have G of S equal to omega n square divided by S square plus 2 theta omega n S plus omega n square. Okay. Here we know omega n is natural frequency. Of the system, and zeta is the damping. So now, just like we looked at system parameters, when you're looking at time response, so you have two components when you're looking at transient time response. Okay, one is transient response, and the other is steady state response. So what does this mean? So if we looked at this plot, right? So this is t time, and this is c of t. You have, this is how a time response, an underdamped time response looks. Okay? So let's say you divide this into this part in the transient response. This part is the steady state response. Okay. So does this make sense? What this transient response and steady state response means?
Is that dash line down? Is that perfectly down the middle? Is that perfectly down the middle? Is the distance between the transient and the steady perfectly the same?
It's not distance.
It's like where it tries to like from the city, that's the transient, and when it becomes city, that's.
So this can keep on going. You should understand this can keep on going. This time can go up to infinity.
So when you put that little line in the middle, middle, was there any significance to where you placed it?
Yes, there's a significance to that. So what does that mean? Tell me what does that mean? Look at the response and tell me what it means.
Which line is it?
Is it after it
Does it
gets-
divide into two phases?
It's divided into phases. Any system you take, when you give it an input, it will respond to whatever desired output. What is a desired output here? The desired output is this dotted line is a desired output. Okay? This is a desired response, and this is the actual response. Okay? No system will immediately get to the actual response. Okay? You cannot get to the actual response, or you cannot get to the desired response in 0 time. Can a system start responding here? Do you understand what I'm saying? Do you understand my question?
One more time, please.
No system will start responding to the desired response. What is a desired response when you're flying an aircraft?
Steady level.
You want to, the maximum, a lot of your response is going to be cruising. Can you immediately start cruising? You have to get to that altitude. That is the transient response. Its response after it reaches that cruising altitude is the steady state response. That you can say is a steady state. Right? So you can think about that. That is a transient response and this is the steady state response. Got it? You understand the significance now? So what we study here is transient response. As part of this chapter, we focus on transient response. And then we study something called, let's look at this transient response. Response characteristics. Or parameters. So what are some of the transient response characteristics parameters you have looked at already? Do you remember?
The overdamped, underdamped, pre-damped.
No. Not the those are the types of responses. Characteristics, parameters.
With the real roots,
Huh?
real and distinct root, real.
Response characteristics. What are response characteristics? Response. You understand response? Everything is clear with response? Right. Okay. So some of the characteristics you looked at is rise time, settling time, right? The time constants. Those will determine how the system will respond. Those are some quantitative qualities which will determine how the system will respond. Okay. So what we do here is we look at similar properties for a typical underdamped second order system, and you can apply this to any second order system. Let's look at this. We have this. Okay. This is the desired response, which is, let's say, 1. So what you're doing is you're supplying. Think about this as a unit step input. Okay, and you want your system to respond to the unit step input by just following whatever it is, whatever that input is commanding. So your system will not just do that. So what it will do is it will, you analyze this, first thing you need to know here is what is rise time. Okay. So rise time denoted by TR is, it's defined in a very similar way. Time taken by the system to go from point 1 to 0.9 times the final response. Okay. I'll give you the formulas for now. We won't discuss how we get the formulas. You can obviously go back and check what those formulas mean. Then you have, so rise time is what? How do you denote rise time?
Rise time.
If on the plot you are asked to depict rise time, what will you do?
You find the derivative.
Huh?
The derivative. You rise over.
You
Yeah,
still,
no,
that,
you're
making it too
that one
complicated.
is CFT, right?
Huh?
That one is, you just saying CFT is one, right? Thank you.
That axis is here.
Okay. And then, okay.
I just wrote it here.
Yeah, it's
It's
just
the same
says
thing.
there.
So what is the time and what is this thing? How do you figure out?
Is 90% of
Huh?
90% of one. 90% of the limit of the final value of the.
So it's this. This is 10%. Okay? This is 0.1. Right? This is 0.9. You agree? So this time, this time is TR. You get it?
That is, you said,
Rise time.
Would you say?
You get it? Everybody's clear on that?
is that the same thing as the derivative?
Hmm?
The change of,
Don't make it unnecessarily complicated. It's simple, so you don't have to think about it like that. Here you have to understand this statement: time taken by the system to go from 0.1 to 0.9 times the final response. What is the final response? What is C of t final?
Oh, I see what you're saying. So, yeah, they don't even know why.
What is this?
Just the time was
This is 1. Okay? So C 0.9 would be 0.9. C 0.1 would be 0.1. That's it. Okay? The time taken. So you can say, you can start the time here and you can end the time here. It's like you start your stopwatch here. When it reaches 0.1% of the final response, you start your stopwatch. And when it goes to 0.9% of the final response, you stop your stopwatch. And then that time is the rise time. Okay. Then we introduce something called peak time. This is represented by EP, and it is time taken required to reach first or maximum peak. Where is the maximum response?
It's that first one,
Huh?
that real tall.
Right.
Which
This peak, right?
Yeah.
So this is the peak of the response. This is the response value will be the highest at this point. Correct? So this is the time taken by the system to reach this peak
So from 0 to
from 0 to
whatever point that
whatever that point is, this peak. Okay? And then you have, so what does first or maximum peaks mean? If you have a couple of the same, this thing, of the same size, if the two peaks are the same, you take the first one. Okay. If it does something like, and then it will do like this, and then it will slow down, you take this peak, the second peak, the maximum. If the two are equal, then you take the first. Otherwise, you take the maximum. You understand? The response need not be like this. Response could be so where is the peak here?
that's second.
This is the peak, right? So otherwise, it could be exactly like this, right? So where is the peak now? The first one.
Well, that third one is really the tall
Right. That's good. Tiffany is active. Tiffany is very independent. That's good. But if you assume that all three are the same size, then you take the first one. Okay? The other one is percentage overshoot. Alright, do one thing. Give me your attendance and now I'll just write down. So only you guys will get attendance, okay? That will your so next time what we'll do is if somebody comes after 8:30 they'll not get attendance. We'll do that. Okay? You can come and attend the class. Alright, there are two more characteristics.
But there's only, what is that overshoot thing? The overshoot, is that one of the characteristics?
Overshoot, yeah.
The what?
Are we just very like
Yeah, we're discussing that.
overshoot that really the lab? We need to understand it. And the rise time and the response time formula does the same apply for the second resolution too?
No, it's different.
Different, right? Yeah, we had that on the homework and we figure out on the lab.
You had that?
Yeah, number 2 was on
Yeah.
and we figure out that's what we're doing.
You might have got the labs mixed up. You might have given us the lab for the next, like after we had finished.
No, I gave you, I think I gave you that because I'll show you what it is actually. If you right click, you'll see all the characters.
So once you draw in like
Yeah, you right click on that. Once you have in MATLAB especially, when you do the step, that plot shows up, right? And then the plot you can just right click and say characteristic. Each characteristic you can just click. It will pop up. So that will
you know
also
like how to do it manually.
Huh?
You know manually we have to do it so we lab.
manually you can just hand calculate, hand
What do
compute.
you know like how to do it?
Huh?
Do you know like how to do the overshoot and the
You can just use a formula in MATLAB and then I'll tell you percentage overshoot.
Because if we use the formula MATLAB, that's technically not doing it manually, you see.
MATLAB itself, when you plot this,
He's talking about the
MATLAB,
pre-lab.
huh?
He's talking about the pre-lab.
Right, then you use formula.
Right. Which we don't.
Is there somebody in the lab, in a computer lab, in bio that's tutoring?
I don't know about tutoring, but I was
Alright, percentage overshoot.
Here, so this is the amount we form overshoot the steady state of final value. Expressed as a percentage. Okay. So this now, let's say this value here C of t is 1.2. Okay. So what is the percentage overshoot? Hmm? Right.
Wait, I don't understand.
The response at each of these values is C of t will have each of these points C of t will have a value, right? If the C of t is 1.2 here, what is the percentage overshoot? What is the amount of overshoot? Huh? 20% compared to the final value. What is the final value? 1. Okay. So it's simply percentage overshoot is
Well, is it like 1.2 is 1.9% or 1.1?
no, it's 20% more
20% more.
percentage overshoot. So the overshoot is this much,
Oh,
right? So you say it's
So basically, we just subtract that final, that those two values, and then whatever, and then convert that to a percent.
right. Okay. So here this is the percentage overshoot. And the final this thing is settling time. The thing with these all these characteristics parameters is what you don't have. Now compare this to the first order, right? First order system. First order system will never have an overshoot. If you look at the first order system will never respond like this. It will slowly go like this. Okay. So this peak time and percentage overshoot will not make sense for a first order system. Got it? That's the reason these were not introduced for the first order system. If you remember, there was a rise time and there was a settling time. The concept is the same for first order or the second order, but the formulas are different.
is it the same for the overdamped?
Yes. So this is for general. Although we are talking underdamped is the most common case. Okay, that is, if you study underdamped, you will understand most of the other systems. Undamped is not an acceptable case. Undamped, you don't want anything marginally stable. Okay, and critically damped, all
all these parameters still apply, right? Under dam system, again all these systems will still apply. What would be the peak time? Peak time would be probably infinity, right? You understand why under dam system, sorry, not under dam, over dam system, why the peak time would be infinity? What is the over dam system? So it will gradually do this, right? Where is the peak? There is no peak, correct? What is the percentage overshoot? It's negative. You understand? See what I'm saying?
It's not like going above the zero or it's negative.
Huh?
It's not going anywhere above that final, it's zero or negative.
You can say 0 or negative, but it is not relevant, right? It will never go to that peak. Go back and look for what is an over dam system.
Over there means it's just.
Yeah.
Oh,
Just
yeah,
like
it's a,
Did you say
It'll
that?
never.
exponential. Isn't that the word?
No, don't look
Am I looking
at
at
it.
the
Just
wrong
look
word?
at the plot and look at how it is.
Huh? So we'll just-
Yeah.
Okay. So just look at how it responds to the final thing. It slowly gets to the final. It will eventually get to the final. It will never go above the final. If it never goes above the final value, it will never have an overshoot.
So you said first order systems are similar to that.
First order systems are similar to over dam systems. That's the reason these two parameters are not relevant. Okay. So settling time, this again has a similar definition. It's simply time taken by the system to reach and stay within 2%. You can change this value as per your convenience. Okay? You can just say, even say 5% of the final value. So, if you think about it, this may be an overstretch, but at this point, somewhere here, what is the value of C of t at this point?
0.9.
You can assume it's 0.9598.
Less than one.
Okay? You can say 0.95 or 98, right? At this point, the system reaches within 2% of the final value. What does that within 2% mean? It can be 1.02 or 0.98. Got it? Within 5% means it could be 1. Huh?
1.05,
0.95. So once it reaches that range and stays with that, the time it takes this is the settling time to get to that steady state. This is important because if you think about your aircraft, you want to reach that steady state as soon as possible, right? It depends on what is your runway length, what is your what city are you in. If you are in a bigger city, you don't want the settling time to be. You want to go above the clouds or at a particular altitude at the earliest and stay there. So this settling time becomes very important. If you don't have that, you cannot fly really slow aircrafts. You cannot fly. Can you fly a passenger aircraft on a aircraft carrier? You know what an aircraft carrier is?
Like the Boeing, like the big Boeing 737.
Huh? Yeah, 737. Can you do it on an aircraft carrier? You know what an aircraft carrier is? Everyone?
I don't think you can.
What is an aircraft carrier?
It's a ship with a whole lot of planes on it.
Yeah, Maybe.
Going to
Maybe.
Yeah. So it's
The 787 is
Yeah.
huge.
huh?
The 787
I
is
was
huge.
thinking about something different.
And even if you think about even just a glider, can you do that on a aircraft carrier?
A glider? You said?
Glider or you know
Can you
just
land
a
an aircraft carrier? Can you land
I've seen
a glider?
some.
passenger, any kind of passenger aircraft, can you take it off of an aircraft carrier?
If you use the downfall.
You
I don't think it'll be enough runway.
Exactly. So you don't have the time.
Yeah.
So that is when you know these characteristics become very important. So you look at these characteristics and design your aircraft carrier. It's essentially a runway on a ship. Right? You cannot have as big a runway you have on ground. It has to be small. So you have to design these parameters so that it can take off in that limited space. Okay. So the formulas, I'll give you some formulas. Just you don't have to memorize these, but you have to be able to show these on a plot. Okay, even for exam, I may ask you to calculate certain things, and at the same time, you will be asked to show these. So you have to be able to plot this, do this plot, and then mark all the different parameters. Only 4 parameters are there. So TP is simply pi over omega n into root of 1 minus theta square. Percentage overshoot is equal to e to the power of minus theta pi alpha root of 1 minus theta square into 100. And you can all derive these formulas if you want. Yes is equal to 4 over.
Is that 5%?
Huh?
Or 0.05%? You put 5, you put 0% and 0.5.
No, that's percent overshoot.
What typing do you done?
I'm
Huh?
still asleep.
Tiffany has to wake you up.
No, I couldn't see it at first. I know that it wasn't a little weird.
She's not awake completely as
She is
Huh?
She is good with it.
well. And PR, what you need to do is, for PR refer table, figure 4.16. There's a formula and then there is there's a damping ratio versus rise time into natural frequency. You have to figure out the the rise time from that. Okay. From the exam point of view, what is important? Given a system, you should be able to calculate all of this. Okay. Compare this. Compare this one. This your system will be like this. Okay. You compare this and this, and you have to be able to figure out all these. So now you understand how to do the pre-lab. It's simple.
Yeah.
Okay. In MATLAB, it will be much more simpler.
Is that negative?
Hmm?
No, it's just as fast.
-4 what?
I thought I was negative.
There's a little speck of marker by that 4.
This one?
No.
No,
Yes. See that little speck of red?
That is it.
What
What does this mean?
That's the system response.
Huh?
And that's the time.
He is not even paying attention at all. He's just.
Settling time.
Huh?
I thought it was
It was system response.
No.
What is it?
Settling.
Settling time. Okay. What is settling time?
Settling time is the time it takes.
Okay. Stop there. Settling time is the time. Okay. Do you know what is negative time?
There is no such thing. Don't laugh.
No.
I know.
All right, let's stop.